All right, welcome back, everybody. Today we're doing section 13.1, entering chapter 13. This chapter is all about vector functions, and we're going to get to explore space curves and a bunch of cool stuff when we go through the only four sections in this chapter. Let me go ahead and pull up the slides, and we'll get started. All right. Good news, this one is actually a bit of a short lecture. There's not a ton of content for this section. Some of the other sections in the chapter are a bit long, though, so we'll get to those in a little bit. All right, for this section, 13.1, we're just going to talk about vector functions, limits and continuity, space curves, and then a little bit of sketching space curves with Mathematica. Hopefully you enjoyed the Mathematica activities we did for 12.5 and 12.6. We have a couple more that we're going to do from this chapter. In particular, 13.1 has a computer lab activity where we'll use Mathematica to plot some of these space curves and things like that. I've got one example of this at the end of the slides, but I'm going to save most of the exploration with Mathematica for the activity time. Okay, so starting off with a definition, what is a vector function? So a vector function, or sometimes called a vector valued function, is just a function whose range is a set of vectors. So the idea is that the output of these functions is a set of vectors. That's a vector valued function. So in this class, the input of such a function will almost always be a real number, but again, really, you can talk about putting almost anything into a function as long as it's well defined. You can put vectors into a function, scalars into a function, functions into a function, as long as everything is copacetic and well defined. But for us, the input is almost always going to be a real number. We're also mostly going to consider vector outputs in V3. Maybe that should be a subscript. But just remember that all of these ideas about vector functions extend to any number of dimensions that you would like to work in. In particular, when you get to linear algebra, you'll study vector valued functions where the range could be Vn, V anything. So a little more specificity here. If we let R be a vector function whose outputs are three-dimensional vectors, then for each t in the domain of R, there's a unique vector R of t in V3. So R of t is the output, and it's the three-dimensional vector. If f of t, g of t, and h of t are the components of our vector function, then f, g, and h are real valued functions, and they're called the component functions of R. And we can write something like this. So this is a good thing to just kind of pause and ruminate about for a minute. We're trying to describe what the output vector of this function looks like, and we can do it component-wise. So this is the output function that describes the x component. This is the output that describes the y component. This is the output that describes the z component. Or you could write it in terms of the standard basis vectors like so. So pretty natural, pretty intuitive. Oh yeah, there you go. So intuitively, one way to think about this is you could think of t as time and r of t as the vector that is produced at time t. And we've actually seen this before. We saw this back in section 12.5 when we were talking about the vector form of a line. But now the idea is that our functions don't need to just be lines. We can describe all sorts of interesting curves and vector functions using this type of a structure here. It doesn't have to be just a line. Okay, so this is one I want you to try. Let's let our vector function be given by these components. And what I want you to do is list the components individually and then find the domain of the function. So first, let me throw up the thinker for a minute. Just think about how you would proceed. Right? And now say something out loud. Get those juices flowing. Say something out loud to whoever, the wall, your hand, your dog, your cat. Give your brain that feedback. And now try to work it out on your own. See if you can list the component functions and then the domain of the vector function itself. And we'll do it together in just a moment. All right, here we go. This one hopefully was not too difficult. The component functions are just right here, t squared, ln of 4 minus t, and root t. So that's what they are right here. You can call them f of t, g of t, h of t if you would like. It's also very common to label these things as x of t, y of t, and z of t. Just a very natural labeling when you're using x, y, and z coordinates. The function itself, the vector function r, is only defined when all of the component functions are defined, right? That makes sense. You can't plug something invalid into this particular component function and still get a valid output for the vector function itself. So what do we need? We need 4 minus t to be positive, and we need t to be greater than or equal to 0. So the domain is going to be the intersection of those two sets. So the domain of our vector function r is going to be the intersection of this and this, which gives us 0 to 4. So this is a particular vector function that is only defined on the interval from 0 to 4, 0 inclusive. All right. Now, let's talk about limits and continuity. So the good news, the good news is that limits and continuity involving vector functions are really just a natural extension of what you've already seen back in Calc 1. Essentially, the limits are just defined point-wise, or I'm sorry, component-wise. So if you want to know the limit of a vector function, you take the limit of each individual component, like so. And this limit only exists provided each one of these limits exist. So kind of what you remember in the past, it's just extended to multiple variables, that's it. Right. So more formally, remember this is like what you first learn in Calc 1, like the intuitive definition of a limit. And then right after that, you start talking about the formal definition of a limit. Good news again, this is essentially the same thing that you saw back in Calc 1. We say that this limit of r of t as t goes to a is equal to the vector v if and only if, for all epsilon greater than 0, there's a delta greater than 0, such that if t is sufficiently close to a, then r of t is sufficiently close to v, in particular within this tolerance. And if you can get this relationship for all possible tolerances, then the limit exists. So it's the same idea from Calc 1, just now it's applied to vectors instead. All right, now here's a fun one. This will kind of dust off those old limit finding skills that you remember from Calc 1. So this is what I want you to try on your own. See if you can compute the limit as t goes to 0 of this vector function r of t, where r of t is defined like so. All right, so think about it for a minute. Think about how you would approach it. Okay, and now say something out loud. What are you going to try? Okay, now try to calculate it on your own. Compute that limit if it exists. Pretend you're back in Calculus 1 right at the beginning of the course, and you're learning about limits, and just treat these as limits, individual limits, and see what you get. All right, now let's do it together. So like I had said just a moment ago, the limit of a vector function is computed by just finding the limits of the component functions. So we need to take the limit as this goes to 0, the limit as this goes to 0, and the limit as this goes to 0. And provided all those limits actually exist, then the limit will be the vector that consists of these three individual limits. So these ones aren't too bad. I kind of showed the work here individually. The limit is the limit of this times I, limit of this times j, limit of this times k. This one is a very straightforward limit. It's just 1. This one might take a little bit of pondering for a second, but this one's going to be 0 because e to the 0 is 1, and then when t is equal to 0, it's 0. This is one that, well, I'll say this. You could compute this limit using L'Hopital's rule, but if any of you took me for Calc 1 or Calc 2, you know my opinions about L'Hopital's rule, which is basically sometimes it's a bit of a heavy machine to use for something that can be computed using far simpler tools. This is one that you actually prove. This limit is a limit that you prove is equal to 1 near the beginning of Calculus 1 without any need for L'Hopital's rule. You can use a geometric argument that proves it pretty nicely. So this limit exists, it's 1. This limit exists, it's 0. This limit exists, it's 1. So this is the limit vector right here, which we can simplify to I plus k. And that's the limit as t approaches 0 of r of t. So this function, this vector function is going to this vector right here, I plus k. Right, now let's talk about continuity. So continuity is also the same as what you remember from Calculus 1, maybe even pre-calculus if you talked about it there. We say that a vector function is continuous at a point A if and only if the limit can be moved inside the operator and you get R of A as the output. So in other words, the limit as t goes to A of R of t is equal to R of A, and that's what continuity is, right? All right. Oh yeah, more specifically, the function is continuous if and only if it's continuous, if the component functions are continuous. So again, it's kind of a component-wise argument. Just see if, the function is continuous in the first component, the second component, and the third component. If it's continuous in all three, then your vector function is continuous as a whole. Right. All right. So now we're equipped to talk about space curves. This is where things get really fun. So this is where you get to kind of flex vector functions and talk about some really much more interesting objects than maybe you saw back in Calc 1 or Calc 2. So start with a definition. Suppose we've got functions f, g, and h, and they are continuous, or they're continuous, real valued functions on an interval I. Then the set C of all points x, y, z in 3 space, where x is equal to f of t, y is equal to g of t, and z is equal to h of t, as t varies throughout I, that is called a space curve. Maybe said a little more simply, the set of points that you get in space as t moves through its interval I, that is what we call a space curve. It's like the image of the function, you could say. It's like the set of points that are produced when you let t pass through the interval I. So that's what we call a space curve. The equations here, these are called the parametric equations of the curve, kind of like we had parametric equations for a line earlier, right? And t is called the parameter, just like we saw before. So in a very real sense, we are really just extending what we talked about earlier in section 12.5. So we're saying, hey, this thing that we've been using doesn't just have to describe lines, it can describe other types of curves, and that's where things get really interesting. Right. Maybe this one won't be as interesting as what we'll see in a few minutes here, but try to do this one on your own. Hopefully this one is not too difficult. Describe the curve that's defined by this vector function. So think about it for a minute, stare at that vector function. Right, and then I'm just going to jump right to this. See if you can describe what this curve looks like in space, in words, with some specific things. All right. Okay, now let's do it together. The reason this one may not be so exciting is because this is exactly the same kind of thing that we saw back in section 12.5. So this indeed is just a line in space. It's a line passing through the point 1, comma 2, comma -1, and you can see that just by looking at these initial values, right? That's the initial point. And then the vector that says which way to go is 1, 5, 6, because these are the direction numbers of this particular line. And that's it. So a line, and we'll see more interesting ones in a minute here, like this one. So this is one that I want you to try to figure out as well. So see if you can sketch. Keep in mind, this is an object in three-dimensional space, a curve in three-dimensional space. So you're going to have to try to draw a picture that's 3D. But see if you can sketch the curve whose vector equation is given by this, and then we'll do it together in a minute. Yeah, what do you think it's going to look like? All right, now say out loud, what do you think it's going to look like? What could it be? Just try to give it some descriptive words. Right, and now try to sketch it. See if you can draw just a quick sketch. One thing that helps me when I'm trying to draw 3D sketches is just to kind of do the axes first, right? This one's X, Y, Z, and then see if you can describe whatever that curve looks like, or sketch it with that as your oh geez, what's the word? I can't remember. All right, now let's take a look at it together. So the first thing is we can pick out each one of these component functions. Let me delete this for just a minute before I go to the answer here. The component functions are cosine t, sine of t, and t. And this is where you really want to try to lean into your intuition a little bit and think about what is happening in terms of each component and then kind of separating the components and looking at what happens in the planes. So x is cosine, y is sine. Well, right away, I know that's circular behavior, right? That's the standard parameterization of a circle. In this case, the unit circle, because the scalar here, scalars are just one. So in the xy plane, it's going to look like a circle. So if I were looking at it from top down, it's going to look like a circle. Now, what is this going to do? So this is telling us that in the z direction, the behavior is linear. So what's happening in the z direction is things are just literally going up if t is positive, or they're going down if t is negative, and when t is 0, you're actually right at z equals 0. So if you combine this behavior and this behavior, what do you get? Well, you get this circular rotation in terms of x's and y's, and then you get this vertical motion up or down in the z direction, so it's going to do this, right? And that's what we call a helix, a circular helix. And here's a nice little figure for it from the book. This just reiterates what I said a moment ago. Here's the x component function, the y component function, and the z component function. The circle is traversed in the counterclockwise direction as usual, and z of t equals t. That's just the identity function, so you just get vertical linear behavior. And this is a helix. There you go. So now you have you have the vector function that describes a helix. And remember, you can use all those things we talked about in the previous chapter to kind of like tweak this helix, right? You can add scalars to this to make it go up and down faster. You can tweak the scalars here to make it more elliptical or make it a larger circle. All of that still applies. Um, Yes, yeah. So maybe this one looks familiar because this is exactly the type of curve that you see when you discuss DNA. So DNA is actually a double helix. It's two of these curves that are basically just phase shifts of one another. So in this particular case, a double helix consists of this curve, but also this second curve as well. And the second curve you can see is really just a phase shift of the circle. So that way it starts at a different point, starts at a different point at the same time. And that's where you get two. Here's one of them. Ah, that was not good. Let's try that again. Here's one of them, and then here's the other. Cool, double helix. All right, so now find a vector equation and parametric equations for the line segment that joins the point 1, 3, negative 2, and 2, negative 1, 3. So this is a little bit of a refresher from 12.5. Find the parametric equation of a line segment. So see if you can remember what that formula is. It was one of the important examples. All right, now try to say it out loud. See if you can speak out loud what that formula was for a line segment. Right, and now try to write it down yourself, and we'll do it together in just a moment. All right, here we go. Okay, so this is the formula. And remember from the previous lecture, what I was talking about is you can really think about it intuitively, right? You can think about it as starting here at this position vector, ending here at this position vector, but then you have to kind of parameterize the scalar itself. So here, this is going to be 1 minus t, and this is going to be t. So if you can remember that general idea of like starting at this vector and ending at this vector, and you've got to basically scale them accordingly, then that can help you remember the formula. And if you forget, just remember that if this is where you're starting, then when t is 0, you should have this only, and this should be completely gone, which is exactly what's happening here. And then vice versa. When t is equal to 1, you should only have this remaining, and this whole term should be gone, which is exactly what's happening here. And then t just passes between 0 and 1. So just like we did in the previous, or back in 12.5, let this be the position vector of of P. Let this be the position vector of Q. And then just plug these into the formula and simplify. There you go. Just like so. And then these are the parametric equations. All right, now let's try one that's a little more interesting. This is one I want you to try on your own at home as well. So find a vector function that represents the curve of the intersection of this cylinder, x squared plus y squared equals 1, and this plane, y plus z equals 2. So more specifically, what you're looking for is you're looking for the vector function that describes this space curve right here. All right? So again, think about this one for a bit. Stare at it, mull it over in your head a bit. All right, now say something out loud about what you have observed. What do you observe already about this curve? And now try to work it out on your own, and we'll do it together in a moment. My hint is think about what we did in the previous examples where we kind of looked at things component-wise and asked what is the behavior in these different directions. That can help you get started. All right, now let's do it together. Okay, so let's see here. First thing that I notice, well, okay, so first thing I notice is something similar to what we saw before, which is the behavior in the XY plane or the XY directions is circular, right? I mean, everything is passing around on this cylinder. This curve lies on that cylinder. So that means that X and Y are going to be going around in a circle like that. So right away, we know that X is going to, and what's the radius here? Oh yeah, the radius is 1. So we know right away that X is going to be cosine of t and Y is going to be sine of t. Now we just have to figure out Z, right? So we've got X and Y, but how do we figure out Z? Well, the good news is if we write this down, X of t equals cosine and Y of t is sine, well, we can use this to solve for Z. Oops, to solve for Z. Substitute that in for y, and then you can solve for z, and then you'll be able to get the parametric equation for z. Here we go. Just like this. 2 minus sine of t. So then in the end, we have x is cosine t, y is sine of t, and k is 2 minus sine of t. Now, before we like dust our hands off and move along, this is one of those times where once you find your parametric equations, I encourage you to go back, look at the curve again, and see if those equations make sense with the curve. So these x and y made total sense, right? We're like, okay, that's a circle. It's going to move like a circle in x and y. What about z? Does it make sense that z has a trigonometric term involving, or does that z involves a trigonometric term? Well, let's look at the curve. It's going like this, this. It does. It does make sense, right? Because if we were to basically look at this thing from the side, what we would see is that the point is going to be going up and then down and then up and then down and then up and then down, right? So there is a sinusoidal component or a sinusoidal behavior in the z direction. So this does in fact make sense, and it is correct. All right. Now, um, as you could imagine, and like I mentioned before in previous lectures, sketching these types of curves and more complicated curves, which are more common, is very, very difficult to do by hand. And we often need several different viewing angles of these curves to get a proper picture of what the actual curve looks like, right? So luckily, we have the technology. Do not do not forget we have the technology to explore these things in greater detail and with more intuition. And so you are again encouraged to use Mathematica in this section, as in the previous sections, to visualize these curves. Do not be afraid to use this technology to help you make sense of these objects. Okay. There's always a time and a place for being able to graph things in 3D. And I also encourage you to try to graph things in 3D. If any of you like to draw or sketch, or if there are any artists out there in the audience, then please use this as a great opportunity to practice drawing three-dimensional curves or three-dimensional objects, I'll say, and so on. But it's not really necessary. So you can always use Mathematica. Desmos 3D is another option, but like I mentioned before, Mathematica is more versatile and we can perform additional computations, just like we did in section 12.6 in the activity when we had those contour maps. And we'll talk about contour maps again when we get to, oh geez, what section is it? Um, I can't remember the section. I think it's somewhere in chapter 14, but I can't remember. That's okay. All right, so let's try this one. We're gonna look at Mathematica in just a moment here, but it says to investigate the space curve given below, and then use the Mathematica command parametric plot 3D to graph it. So here's what I want you to do for this one. I really, really want you to try to lean into your intuition a bit here and look at these component functions and ask yourself how that affects the behavior in those particular directions. What's happening in the x direction? What's happening in the y direction? What's happening in the z direction? So look at these, mull them over in your head for a bit, and then you know what I'll ask next. Say something out loud. Give your brain that oral audio feedback, that audio feedback. Okay, and now, you know what I think I need? Now I think I need like a little, I need a little Mathematica icon down there to say like, try to graph it in Mathematica now. So maybe I'll do that next time. But yeah, try to sketch this in Mathematica using this command, and then we'll take a look at it together. Okay, so let's start with the first part of the question. The first part of the question says to investigate this curve, and I had said to kind of lean into your intuition, so I want to do that here for a minute. Now, what I notice first, I'm going to use a highlighter here, is that for x and y, there's this cosine and sine factor. So because those factors are present, that means there's some kind of circular behavior going on. Circular, possibly elliptical, really just sinusoidal behavior. There's some kind of like oscillation, some kind of repetition, some kind of periodicity, right? There's a periodicity going on in terms of x and y. There's also some kind of periodicity going on in the z direction. So the curve is doing this if I look at it in the z direction, right? Now, where things get really interesting is these other factors here, this and this. So think about this for a minute. This is where things get really interesting. Um, we've already got the notion of circular behavior in the XY plane, right? However, this essentially is scaling the radius of that would-be circle, right? That would-be circle. If these weren't here at all, and you just had cosine t, sine of t, you would just have a standard circle of radius 1 spinning around like this, right? But now there's this, oops, there, yeah, now there's this scalar going on. So what this does is this affects the radius of that potential circle. Now, luckily for us, these are both the same value, right? So look closely at these two values. Let me highlight them again here. 4 plus sine 20t, 4 plus sine 20t. That's helpful information because what that means is that the scalar is the same for both the x behavior and the y behavior. So that means we are seeing circular behavior in the x and y direction, and it's the same. So it's not elliptical, it's circular, right? What else do we got here? Let's see. Okay, so one thing to keep in mind is we've got circular stuff going on, but then we also have this going on in terms of z. So z is still going up and down. So try to put these together in your mind, like, lean back, close your eyes, just like stare at the wall or stare at the inside of your eyelids, and just think about spinning around in a circle, but also going up and down while you do that. So like, kind of like this. Right? That should be something like that should, if you look funny, that's okay. That's basically what it looks like. However, there's more because this is also oscillatory behavior. So not only is the radius the same, so we get a circular behavior, I'll say globally in terms of X and Y, we're also getting these wiggles as we go around. So we're getting these like wiggles as we go around in terms of X and Y. We're also getting these wiggles up and down, right? So we're getting these like circular wiggles as we go around, but we're also going up and down like so. And if you put all that stuff together, what you get is what's called a toroidal spiral. A toroidal spiral. And this is what we're going to look at in Mathematica right now. So let me pull that up here. Here we go. All right. There we go. So can you see it? Yes, it's all set up. This is just the command parametric plot 3D. What I did was I entered the components right here. These are the component functions. Here's that radius cosine t, radius sine t, and then cosine 20t right there. Right, and then we're just going to do from 0 to 2 pi. You can always alter the constraints on the parameter if you wanted to see more or if you wanted to just include more. I'm going to hit Shift Return, and there it is. Same picture you saw on the slides. Let me blow this up a little bit. There we go. And now think about what I was saying a moment ago. So this is where you want to use this technology to help reinforce your intuition, right? So the first thing that I had said, I'm going to turn it vertically like this, was it would look roughly circular in terms of x's and y's, which makes sense because again, up here we've got cosine t, sine of t, and the radius scalar here is the same in both. So we're getting circular behavior in the x and y projection, right? But because this radius, even though it's the same for both, it's also got sinusoidal behavior built in. There's going to be wiggles as you go around. Remember, this is me going like this with my finger, right? That's what's happening. Wiggle, 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 wiggle as you go around. And then there was this cosinusoidal behavior, I'll say, in the z direction. So if I turn this up like so, and we just look at it from a side view, you see, there you go. You see exactly what I was saying there as well. Let me tip that down. It's going up and down as you go around in a circle. And the reason this is called a toroidal spiral is because it's in the shape of a donut. A fancy word for a donut shape is a torus. And what you can see is this curve basically lies on a donut. So pretend there's a donut in here. And this is like, maybe you could think of it as the trajectory of an ant as it walks in like circles around the donut, that kind of thing. This is like the path that it would take. The fact that these things are the same, like these radiuses are the same, this is what's giving you these circular projections. I don't know if you can see them like right here. Hold on. Make it a little bit bigger. You see how there's a circle here? And there's a circle here. Well, if these values were not the same, then what would happen is you would not have circular cross sections here. You could have elliptical cross sections or something. If it was a little bit different, it would be slightly different. Maybe let's mess around with it here. Let's do like 2 times just for this part. Oop, up, oop. Hold on, I'm gonna try this again. Oop, let me see. No, I don't want the mesh. Where's more viewpoint above? There we go. Yeah, so yeah, just delete this one. So what happened when I scaled the X component here is it got squished. It got stretched, I should say. Stretched in this direction, squished in this direction. So now it's not circular, it's elliptical, right? But you still have those wiggles. So you can also alter things here. Like if I added a scalar here, did like 2 times this. Oh, now things are getting very elliptical. So now you're getting these ellipses. So notice now the side, man, the side view. Hang on. Let's try this again. Viewpoint front. There we go. Now you can kind of see it. So before we had circles, right? Now we've got squished circles. Now we've got squished circles because things are basically, they're not giving you circular behavior anymore. You're getting elliptical behavior. Cool stuff. And if we were to scale this, for example, if we were to scale this cosine, that's going to scale the sinusoidal behavior in the z direction also. That's the idea. So again, I encourage you to play around with Mathematica, play around with these types of diagrams, look at them, turn them around, mess with these numbers just to help build some familiarity and build some intuition for what these things look like. All right, let me go back to the slides. Okay. Yeah, there we go. All right, and I think that's it. So let's play. Like I said, this one's pretty short, so it's nice when there's a short lecture every now and then. I won't dwell too long. There's more lectures to watch this week. So thank you again for watching, everybody, and I will see you next time.